simplest way or most naive way to do m g to the power of e modulo n. So Lido is saying the naive thing to do is multiply g times e, g times g times g times g times g, and you do it n time, and you do it e times, and then you can reduce it, or you can you can do the modulo after you multiply or at the end. You do g times g times g times g times g. What is the running time of this algorithm? How many multiplications do you do? You can do you do a lot. You do an exponential amount of multiplications, right? So this could be a very, very lengthy operation. And now I must remind you that modular multiplication is not so cheap. Multiplication is cheap. Modular multiplication is as difficult as division. That's correct. Modular multiplication costs as much as division because you have to take the remainder. To take the remainder, you need to divide. So again, if you do 2 to the power of 1024 modular exponentiations, that's going to be very expensive and it's not reasonable to do. Okay, so you're not going to do it 2 to the 1,000 times. So I would like to find a way to do this effectively in an implementation. And there are two approaches to doing this. Again, the Handbook of Applied Cryptography is an excellent guide to do this. It has up to pseudocode. I'll show you some. And the two general approaches to getting ModX done quickly is either doing fewer multiplications or making the multiplications cheaper somehow. So they don't cost as much as a division, or maybe they cost like half of a division, or maybe they cost a division half of the time, or something like that. And I will show you some tricks to do it both this week and next week. And of course, the right thing is to do both fewer modular multiplications and have them really cheap. So I think that considering the time, I'm going to tell you how to do fewer multiplications tonight. And next week, we'll talk about how to make them cheaper. So the objective is to go from 2 to the 1,000, 2 to the power of 1,024 exponentiations to go to a lower number. And now we're going to open the Handbook of Applied Cryptography, which is not the most interesting book, but it's very, very important to know how to use it. And we're going to turn to chapter 14, and there we're going to find an algorithm called left-to-right binary exponentiation. And what this algorithm does is it doesn't require 2 to the power of e multiplications, but only e multiplications. And how does it work? We're going to start. We want to output g to the power of e. So we're going to take our number and square it, and square it, and square it, and square it. Every time we square it, we get one more bit in the exponentiation. But the bit we get is 0. I'm going to show it to you in the chat, no problems. But then I'm going to multiply it by g sometimes to make sure the ones get back in. So I'm going to show you in the shared notes. I hope it works. Now I'm going to raise some kind of number. So let's say I'm not going to say what g is equal. G is equal to something, and I want to say that e is equal to binary. Okay, this number. Everybody see the public chat? Because I'm on the shared notes now. Can everybody see the shared notes? Okay, great. Fine. So I want to calculate g to the power of e. I don't know what it is. So the naive thing would be to do G times G times G. Uh, yeah, yeah. This is what is it? 7? No, it's 1 times it's 5 plus, what number is this? Yeah, what number is this? It's 21 maybe? I think it's 21. Yeah, so 21. So this is equal to 21. So I don't want to do this 21 times. This is expensive. So to do it using left to right, I'm going to start with A is equal to 1. Okay? And 1 is actually equal to G to the power of 0, if you think about it, right? Because any number to the power of 0 is equal to 1. And now what I'm going to do is I'm going to square the number. And this is going to make it equal to G to the power of 0, shift left, 1. Let's do it slowly. So it's going to be equal to the power of G, 0 times 2, okay? Because if I square it, which is equal to G to the power of 0, shift left, 1, I'm going to do it in binary, which is again equal to this doesn't really make a difference, right? And then I'm going to look and see if this bit is 1. If it's 1, I'm going to multiply it by G. So this value is indeed 1. I'm going to underline. So this is 1. And then I'm going to do A is equal to A times G, which is equal to G to the power of 0 plus 1. Okay? And this is equal to G to the power of 1. Are we okay so far? Are we okay? Can I keep going? Okay, fine. So now the next bit is 0. So the next bit is 0. I'm going to do A is equal to A squared, which is G to the power of 1, shift left 1, which is equal to the power of G to the power of. Okay? And now I'm going to look at this bit. It's 0, so I'm not going to skip it. And then I do it again. It's going to be G to the power of, right? And then I do A times G. It's going to be G, it's going to be equal to G to the power of. Just to make sure that the two operations I'm doing, squaring is equal to shift left of the power. I'm just shifting everything to the left because I'm multiplying by 2, binary shift left. And multiply is just adding 1. So I'm taking this binary representation, and I'm shifting and multiplying, shifting and multiplying. After I finish shifting, I can get the entire value out. So Oren is asking, what about the modular? So indeed, I need to take care of the modulo somehow. And there are two approaches to doing this, and both of them are not optimal. One approach is every time I do a multiply, I can take the modulo, which means I'm paying as much as a division every time I do a multiplication. The other option is to do a modulo once in a while. Just you have to remember that you can do modulo as many times as you want. It doesn't change the result. So if I do modulo once in a while, I save on divisions, but now the numbers that I'm multiplying are larger. And multiplication is quadratic in the length of the inputs. So each multiplication takes a longer time. And I also need more memory to do it. And these are very large numbers. So there's a trade-off. Usually what you do is every time you multiply, you take a modulo, and this is how it's going to work. So how many modular multiplications do I do in this algorithm? What is the answer? In the old one, I did 2 to the power of e, 2 to the power of e. That wasn't so good. But here I'm doing 2 to the power of t. Sorry, t is the length of. So yeah. So it's the number here. The length of e is it's t bits. So it's O of t. If I'm more precise, the best case is going to be t, and t plus, yeah. You know what? 1 squared is 3. So it's either the best case is going to be t, and what is the worst case going to be? 2 times t, right? If all the bits are 1, that's the worst case. And again, when you're choosing how to do RSA, there are tricks to find values with low Hamming weights, with a low number of 1s, so it's going to be faster. But it's between t and 2 times t. And now I'm going to do an example. I think I can do an example. Here's an example. So we want to calculate 7 to the power of 6. So we're going to start with a, and a is equal to 1. And so let's see if it works. I'll do it in the chat, in the notes. Where's my mouse? So I want to calculate 7 to the power of 6. 7 to the power of 7 to the power of. So it's going to be 7. It's going to be 1 times 1 is equal to 1. Fine. And then I do 1 times 7. 7. And I do 7 times 7 is equal to 7 times 7 is equal to 4. And then I do 4 times 7. Right, because there's a 1 there, so I do 4 times 7. And this is equal to, believe me, that is 13. And then I have to, thank you. Oh, autocomplete. Autocomplete. Wow. And then I do, let's try this one again. And so now I have to square this. I do 13 times 13. It's not working. So I'll do it myself. Ah, thank you. And then I need to do 4 times 7, which is equal to 13. I know this one. And in the end, I do 13 times 13, which is equal to 4. Thank you. Correct. And again, 7 to the power of 6 modulo 4. It's pretty easy to calculate because 7 to the power of 6 is actually 7 to the power of 6 is equal to 117649. And just ignore, because when you remember the psychometric, right? If you want to find, oh, it's modulo 15. Right, and then we do this. How much is this modulo 15? It's going to be, yeah, it makes sense because it's a 4 here. Yeah, definitely it's the right answer because 9 is something plus 4. And I'm optimistic about the rest. Right? So this was a nice implementation of modular multiplication. And how many multiplications do we do here? This is 3, so it's 1, 2, 3, 4, 5, 6. 6 is better than 21. It's a good number. Okay, so thank you to all of my autocomplete team. Now, I can do it even faster. And to do this, I open again the Handbook of Applied Cryptography. And there are ways of doing it with less multiplications and the idea is that to do some pre-computation. The pre-computation it's a reasonable thing to do because you know what your keys are, so you can prepare yourself to say, I'm going to be encrypting a lot of data using this key, or decrypting a lot of data using this key, so it's fine. So one of the ideas is what's called the addition chain method. One of the ideas, the window method. The window method is that you don't do only squaring, but you can do you can add, instead of 1 bit, you can add 3 bits. So you calculate to the power of 2, 3, 4, 5, 6, 7, and 8. And then you can do it in one multiplication. And then you do it again and again and again. So it's cheaper, but again, the handbook of applied cryptography is going to be your friend in doing this. So OL, OL, we can do the modulo whenever it works for our implementation. We're going to do it. Usually, you do it after each multiplication because these numbers are very, very large. Okay. So now we have as few multiplications as possible, but still, modular multiplications are very, very expensive because they cost as much as a division. And we don't want to do divisions. So how do we get multiplications to be cheaper? So one cute trick, which I'm not going to go into details in this course, in this hour, but in a few weeks we'll go into more details, is the Chinese remainder theorem. And here it is written in Chinese. But the idea is that there will be more discussion about this when we talk about fault attacks. But the idea is that instead of doing it modulo n, you're going to do it modulo p and modulo q. And modulo p and modulo q are half the size. So multiplications are a quarter of the time because it's quadratic, right? So I do it modulo p, I do it modulo q, and then I do CRT, which I don't explain right now. I will explain it when we come to it. To combine the two, so reduction going to mod p and mod q costs like one modular division, and going back is one modular multiplication again. And p and q are very cheap, so this is a very reasonable thing. Everybody does CRT. But again, now I modulo p or modulo q, and my multiplication still cost as much as divisions. And now, what do I do about that? And what do I do about that is called the Montgomery reduction. And the Montgomery reduction is not, it's not the right time to discuss. It's very late at night. So next week, we will start with the Montgomery reduction, and we will attack RSA with Montgomery reduction using a timing attack and get a key. So thank you, everybody, and I wish you best of health, and we'll see you all next week. Bye-bye.
Yossi, I can ask you a question?
תן את ההקלטה, שלא ישמעו את האנגלית שלי שנייה.